Hello students, this is Usha from G.K.Jain High Secondary School. Today we are going to see the electrostatic part 4 in 12th standard physics. In this chapter, we are going to see about the Gauss law and its applications.
Electric flux. The number of electric field lines crossing a given area kept normal to the electric field lines is called electric flux. It is denoted by the Greek letter 5e. The SI unit is Newton meter square per coulomb. Electric flux for uniform electric field. Consider a uniform electric field in a region of space. Let us choose an area A normal to the electric field lines. Phi E is equal to EA, which is shown in the diagram A. Suppose the area A is kept parallel to the uniform electric field, then no electric field lines pierce through the area A. So the electric flux for the case is 0. Phi E is equal to 0. If the area is inclined at an angle theta with the field, then the component of the electric field perpendicular to the area alone contribute to the electric flux. So in this case, phi E is equal to E cos theta into A. Suppose a closed surface is present in the region of the non-uniform electric field. Phi E is equal to closed integral of E dot dA. The electric flux is negative if the electric field lines enter the closed surface and positive if the electric field lines leave the closed surface. Next we are going into the topic Gauss law. Gauss law states that if a charge Q is enclosed by an arbitrary closed surface, then the total electric flux phi E through the closed surface is phi E is equal to closed integral E vector dot dA vector, which is equal to Q enclosed divided by epsilon naught. Here, Q enclosed denotes the charges inside the closed surface. Discussion of Gauss law. The total electric flux to the closed surface depends only on the charges enclosed by the surface, and the charges present outside the surface will not contribute to the flux. The total electric flux is independent of the location of the charges inside the closed surface. The shape of the Gaussian surface to be chosen depends on the type of the charge configuration and the kind of symmetry existing in the charge configuration. In the left-hand side of the equation, the electric field E is due to charges present inside and outside the Gaussian surface. But the charge Q enclosed denotes the charges which lies only inside the Gaussian surface. The Gaussian surface cannot pass through any discrete charge, but it can pass through continuous charge distributions. Gauss law is another form of Coulomb's law, and it is also applicable to the charges in motion. The next one is applications of Gauss law. Electric field due to an infinite long charged wire. Consider an infinite long straight wire having uniform linear charge density lambda. Let P be a point located at a perpendicular distance from the wire. The electric field at the point B can be found using Gauss law. The electric field between the two charge elements point radially away from the charged wire, and the magnitude of electric field is same at all the points on the circle of radius r. From this property, we can infer that the charged wire possesses a cylindrical symmetry. So, let us choose a cylindrical symmetric surface of radius r and L as shown in the diagram. So, the total electric flux in this closed surface is calculated as follows. Phi E is equal to closed integral of E dot dA vector. So, which can be, when we have the closed integral, we can make it as three parts. One is the curved surface, another one is top surface, and third one is your bottom surface. So, we have three integrals over there. So, if E is parallel to A and E dA is equal to E into dA. For the top and the bottom surface, EA is perpendicular to A vector and E vector dot dA vector is equal to 0. Substituting the values, we get phi E is equal to integral of closed surface E dA is equal to E Q enclosed divided by epsilon naught. Since the magnitude of the electric field for the entire curved surface is constant, E is taken out of the integration and Q enclosed is given by Q enclosed equal to lambda into L. Here, phi E is equal to integral of the curved surface dA, which is equal to total area of the curved surface, which is equal to 2 pi RL. Substituting the value, we get E into 2 pi RL is equal to lambda L divided by epsilon naught. Cancelling L on both the sides and substituting, E into 2 pi RL is equal to lambda L divided by epsilon naught. Cancelling L on both the sides, E is equal to 1 by 2 pi epsilon naught into lambda divided by R. In vector form, E vector is equal to 1 by 2 pi epsilon naught lambda divided by R into R cap. The electric field due to the infinite charge wire depends on 1 by R rather than 1 by R square for a point charge. The equation indicates that the electric field is always along the perpendicular direction R cap to wire. In fact, if lambda is greater than 0, then E vector points perpendicularly outward for the wire, and if lambda is less than 0, then E points perpendicularly inwards. Electric field due to an charged infinite plane sheet. Consider an infinite plane sheet of charges with uniform surface charge density sigma. Let us consider a point P at a distance r from the sheet. Since the plane is infinitely large, the electric field should be same at all points equidistant from the plane and radially directed at all points. A cylindrical shaped Gaussian surface of length 2r and area A of the flat surface is chosen such that the infinite plane sheet passes perpendicular to the middle part of the Gaussian surface. Applying Gauss law for the cylindrical surface, phi E is equal to closed integral of E dot dA. So in the same way, the closed integral for the three parts we can use it. One for integral of curved surface E dot dA plus integral of at the point P E dot dA plus integral of P dash E dot dA, which is equal to Q enclosed divided by epsilon naught. The electric field is perpendicular to the area element at all points on the curved surface and it is parallel to the surface area at P and P dash. Then phi V is equal to integral of E dot dA plus integral of P dash E dA, which is equal to Q enclosed divided by epsilon naught. Since the magnitude of the electric field at these two equal surfaces is uniform, E is taken out of the integration and Q enclosed is given by sigma A. We get 2E into integral of P dA is equal to sigma A divided by epsilon naught. The total area of the surface either at P or P dash can be written as integral of P into dA is equal to A. Hence, 2EA is equal to sigma A by epsilon naught. Cancelling A on both the sides, E is equal to sigma divided by 2 epsilon naught. In vector form, E vector is equal to sigma by 2 epsilon naught into n cap. The next one is electric field due to two parallel charged infinite sheets. Consider two infinite large charged plane sheets with equal and opposite charge densities plus sigma and minus sigma, which are placed parallel to each other. The electric field between the plates and outside the plates is found using Gauss law. The magnitude of the electric field due to an infinite charge plane sheet is sigma by 2 epsilon naught and it is point perpendicularly outward if sigma is greater than 0 and point inward if sigma is less than 0. The electric field are in the same direction and the total electric field E inside is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught, which is equal to sigma by epsilon naught. The direction of the electric field inside the plate is directed from positively charged plate to negatively charged plate and it is uniform everywhere inside the plate. The other application is the electric field due to an uniformly charged spherical shell. So when we're going for the spherical shell, we have three parts. One is case A at a point outside the shell, and case B at a point on the shell, and case C at a point inside the shell. So now we are going to see the case 1 at a point outside the shell. Let us choose a point P outside the shell at a distance r from the center. The charge is uniformly distributed on the surface of the sphere. So consider a spherical Gaussian surface of radius r, and the total charge enclosed by this Gaussian surface is q. Applying Gauss law, integral of Gaussian surface E dot dA is equal to q by epsilon naught. The electric field E and dA point in the same direction and at all the points on the Gaussian surface. The magnitude of E is also the same at all points due to the spherical symmetry of the charge distribution. Hence, E integral closed integral Gaussian surface dA is equal to q by epsilon naught. But integral closed integral Gaussian surface dA is equal to total area of Gaussian surface, which is equal to 4 pi r square. Substituting E into 4 pi r square is equal to q by epsilon naught, where E is equal to 1 by 4 pi epsilon naught q by r square. E is equal to 1 by 4 pi epsilon naught q by r square into r vector. The electric field is radially outward if q is greater than 0 and radially inward if q is less than 0. Case B. At a point on the surface of the spherical shell, that is small r is equal to capital R. The electric field at the point on the spherical shell r small r is equal to capital R is given by E vector is equal to q by 4 pi epsilon naught r square into r cap. Case C. At a point inside the spherical shell. Consider a point P inside the shell at a distance r from the center. A Gaussian sphere of radius r is constructed. Applying Gauss law, integral of Gaussian surface E dot dA is equal to q by epsilon naught. Since it is a sphere, so the area can be given as 4 pi r square. So E into 4 pi r square is equal to q by epsilon naught. Gaussian surface encloses no charge, so q is equal to 0. The equation becomes E is equal to 0. The electric field due to the uniformly charged spherical shell at all points inside the shell.
Thank you, students. You all have learned about the Gauss law and its application, and we'll meet in the next video.